Are we back? Anyone there?
Yes.
Alessa, did you want to share your screen, or has anyone started working on this? Oh, okay, go ahead.
I just think. Okay, maybe I can share them. Okay.
You maybe zoom in on that block to see what it's doing.
Yes. Maybe.
So, okay, so you're trying to put together,
yeah. Actually, the function is just here. We are trying to construct the rotated DCM, which project the axis of the momentum exchange device in the body frame.
Yes.
So we know that the orientation of this axis changes with time as a function of gamma, which is a control variable. In this function as an input, the initial orientation of the axis of the momentum exchange devices in the body frame, which are defined in the initialized function.
Yes.
And it also takes in input the angle gamma, which is the rotation about the gimbal axis. And so from the equation that I think I have right here, okay, yes. We have basically written this expression for each of the three momentum exchange devices. So we have the tangential axis, the spin axis, and the gimbal axis as a function of the time. So simply a function of the angle gamma. Maybe I think that this is an error because gamma are okay.
So the initial conditions I gave you are for three momentum exchange devices, as I believe they were all aligned with the spin axis about X, Y, and Z. So one was X, one was Y, one was Z, right? In the body of the spacecraft, something like that.
We can check. We can check, but yes.
Yeah,
yes.
Yeah.
This one. Okay. So I just need to put it together as G0, which is G10, G20, G30, and same for the spin and tangential axis. Okay. This noise around is disturbing. You hear some noise from me, or the audio is just fine?
The audio is fine.
Okay, perfect.
What are these additional variables that you're defining?
Yeah, okay, just because the function here, not this one, but okay, this one takes in input the three gimbal axis and the three orientation of the gimbal axis, spin axis, and tangential axis. So just to make the block more compact, we have arranged in a single vector, in a single matrix.
Okay.
And so maybe that's it. So once we have the three axes, of the three wheels expressed as a function of the control variable gamma, we have to build the DCM. So these are the unit vector of the body reference frame, so B1, B2, and B3. And to construct the DCM, whose elements are simply the scalar product between the unit vector of the body reference frame and the unit vector of the axis of the wheels, which just have written in this way. Maybe now we can check the expression. So the first component is dot B1 is dot B1, the gimbal axis of the first wheel, dot B2 gimbal axis of the first wheel, and dot B3 and the gimbal axis of the first wheel. Same for the spin axis and tangential axis. And same operation for the second and third wheel. I think that's it. So now where we are in the block. So we just need this input and gamma, which is actually a control variable. We can now think that it's a constant. We need gamma in input to this function.
Yeah, for now you don't have it. Will be part of the control law, so you can put a sine wave, something.
Okay.
No particular preference really.
Okay, so just let's make it constant and then you can see.
Yes, well.
Okay. So it's actually triangle because we have one for each wheel. So we have now put some of the elements that we need to express the torque of the momentum exchange device.
Mm-hmm.
So what we need now, I think that we need the expression of C dot. Yeah, let's see if it appears here.
Which one are you looking for?
I don't know if we need the expression of C dot J for the momentum of the momentum exchange, for the torque of the momentum exchange device.
So you want to look at the final total equation and what it requires?
Yeah, maybe it's this one.
Yeah.
Okay.
I don't think you have C dot. I mean, it's been this has been developed so that C dot has been expressed in as a function of other things. Yeah. So probably not.
Okay. So let's check what we have. This is the inertia matrix. This is the rotation matrix that we have just built. This is a constant because it's an input. These are the inertia matrix of the wheel. This is coming from the integration of the dynamics of the spacecraft. And this is a constant. The unit vector ST and J are the output of the function that we have here. So we have it. And let's see what else. Gamma to dot, which maybe, I don't know if it comes from the control law or we need to perform a numerical derivative.
Yeah, actually, it's actually the gamma dot that comes from the control law. So gamma will be an integral of gamma dot. So you can already start putting in the the gamma dot and an integral in front of it, and eventually you will have initial conditions. Well, actually, you do have initial conditions. I think I gave you the initial conditions for gamma, so.
Yeah.
So you can definitely put an integrator right there with the correct initial condition coming from the initialize, and then the gamma dot for now we don't have the control law yet. So.
Okay. Maybe it's the other block. It's numerical derivative.
Why? No, I don't think so. What for?
We have gamma.
Well, no, you have. So from the feedback controller, once we implement the actual control law, you will come in with gamma dot.
Okay. So
yeah.
We have to change this one.
Mm-hmm.
So here is the integrator. Okay, now it's clear. So we, for now, can say that gamma dot is constant and equal to 0, 0, 0. And no, actually, no. Okay. So this is the initial condition. 0, 0, 0. Okay. And so where is the input? This is gamma dot, which come from the controller.
Mm. And what did you put in the initial condition? Sorry, I wasn't.
Yeah, 0, 0, 0. Yeah, maybe I have to check the name of the initial in the initialize, but the value, these are the values, so I think that we can adjust later.
So this block that you're creating, and you may want to change the name because it's not obviously the Euler's law.
Yeah, because
that's fine.
I copy.
Is this so? This is doing everything for the three of them, right?
Yes.
Okay.
Actually, AT, AS, and AG are not vector but matrix. Matrices in which each column is for the width.
Yep.
Okay. So. We need omega j.
Yes.
And this is another control variable.
It actually also comes in as omega j dot, so you have to integrate that, and then you use omega j.
Okay, so
you don't actually you don't need it for that block.
No. I think that this block, which is not the other block, okay, only output the DCM, but obviously we can make all in. We can express this equation in this block. We are thinking to put in different block, but maybe this complicates everything. So we can express the moment, the torque of the momentum exchange device here in this function.
Okay.
So we need, so if we do this, we need the value of the angular velocity of the body in input. So maybe let's see here. Actually, we need both omega and omega dot, maybe. Yes. Okay, so we have here omega dot and omega.
The omega of the spacecraft.
Yeah.
Right.
Okay, let's just change name omega dot b and omega b. Okay. So let's see. We need an input. I have to check initialize what their name are, but we need the inertia of the momentum exchange device. So Y is the inertia matrix, and yeah, Y is inertia matrix, and this is the inertia, the moment of inertia about the spin axis, right? I don't remember the notation. Okay.
And I apologize, I don't have units in this initialize. That's a terrible thing. But they got kilograms meter square.
Kilograms meter square. Okay. So
yeah, I should have done a better job.
ISW and Y. Okay. So we need here need Y and ISW. Let's save it and let's put it as a constant. Oh, it's a mess. Okay.
So yeah, the way I had, I think I had the function that does only the GST axis and the rotational matrices, and then other stuff was separate. But I mean, it's up to you.
No,
so I guess,
maybe.
So you're trying to put so you're trying to put the
yeah.
dynamics in here, the entire thing in here.
Yeah, but maybe it does not work. No, it's better to separate it. No?
As you prefer, it's your model, no?
No, yeah, I prefer to separate because things becomes too complicated and we can lost in it.
Yeah, it becomes a lot of inputs and outputs, so.
Yeah. So let's just cut it. Okay. And let's make another block. So, okay. And we have omega dot. So let's see. Maybe here. Okay. So omega dot. And then omega. And then these other two are constants. So this is Y. And this is ISW. Okay. Then what we need. We need gamma dot. So this can come from here.
So what is that block that you're putting together now?
Yeah, yes. I am trying to write the expression for the torque of the momentum exchange device. So now I think that it's all the dynamics of the spacecraft.
So you eventually want to output from that block the omega of the spacecraft dot, so that you can numerically integrate it.
Yeah.
So you take this equation, you put everything to the right-hand side, and then invert that matrix that multiplies omega body dot, basically.
Yeah, so we have this term J plus is inverted.
Yep.
And then we have to change all the sign of this term here.
Yeah.
So I think that I have to modify it because I actually made a mistake because I just have the block which implements the Euler law. So I think I can delete this. And what comes out from here is E omega of the body, E omega dot. So here there is the integrator, which outputs omega of the body. And we can internal, okay. Oh, Riccardo, sorry. I just have to, I forgot it. There is una seduta di laurea, which I have to attend right now. So maybe I can send this this model to Marco, and he will continue.
I follow
I'm very
you,
sorry.
so
I'm very sorry, but I just
forgot. Go.
Ok, thank you.
Yeah.
Marco, ti invio questo.
Sì, dovrebbe non essere necessario perché ti ho seguita, quindi
Ok,
continuo
thank you. Sorry, Riccardo, I'm very sorry, but
Ciao. No problem.
I completely forgot. See you later. Bye.
Yeah.
Okay, I share mine. Okay. So omega dot b from the integrator takes the omega b vector.
Wow.
So this one.
You are ahead.
Sorry?
You're ahead of the game, it looks like. No?
No, I didn't understand, sorry.
Oh, that you're much more advanced in this development. It seems like, I don't know.
Probably at the same points.
Okay.
Maybe just some two steps further, but I think that so we have the C1, C2, C3, S, U, and Y, omega B, omega dot B, and I take the equation. Put the equation on the other screen. So, well, maybe it's better to comment in real time. Here, there. Okay, so J, also J. Need another input that is J.
Yes.
And then, yeah, okay. Omega dot comes from the controller. I think that's
the gamma dot.
We have the gamma dot as an initial condition. So integrate is gamma. So is a
yeah, you can do a numerical derivative or just drop it. I mean, it's
numerical derivative of this.
Most CMC controllers don't really even include it, probably.
because those are the outputs of the controller, right?
Right.
When we J gamma dot 2 dots. Then dots. Okay, G. We have G. We have this one. Omega dot. Yeah. Okay. It's. Okay. I think it has the torque. Okay. I think that as inputs we almost defined all what we need, but probably when I will write the equation. So
the S, T, and J, they're part of the.
These are this one.
Yes.
That are for us are metrics for each wheel.
Okay.
So I also add the S and G and the torque, right? Mm-hmm. Okay.
Did you try to run it?
No, because I have a problem with Simulink that doesn't display in automatic the new inputs when I change inside the MATLAB function. And so I Control D and but I have to compile. And
oh yeah, if you save only, it doesn't do it.
Probably yes.
I don't know.
It's then save. Oh
yep.
yes.
Yeah.
Wow.
Yeah.
It's
May save you the pain of
yeah, no, compiling.
Yeah.
Okay.
And probably you're missing capital omega and capital omega dot.
Yes. Thank you. Capital omega and capital omega dot. Yes. This function is becoming quite bigger in terms of inputs. Probably can I? No. Split in some way. I don't know. No. How can I name omega? I have to clean up all this one.
That's
project.
Fine. So one thing that I used and you've seen in my model is the go to and from to. So you don't have all these lines all over the place. Eventually you may want to clean it up. I mean, it's up to you.
Yeah. It's a good solution. I'm also a fan of go to from. Yes. Okay. Okay.
So while he's working on this, connecting things, a couple of, I guess, announcements, not really. Well, I have to eventually give you guys a grade. So if you can send me your homework 1 without gravity gradients, just the bare, homework 1 assignment with the quaternions, ordered angles, and then the extraction of the ordered angles from quaternions. That would be great. If you want to send it over this weekend, that's even better. So yeah, that's the one. For this assignment, of course, I'm hoping that you all are starting to work on it, or you have already. And we'll do our best to be done by Wednesday so that you can be done with the class by Wednesday. That's my goal. But if you need more time to finish it, you can do that as well after Wednesday, if that sounds like a plan. Yep. So the majority of next week will be dedicated to this, to finish it together. I would probably ask Mr. Grasso to continue on his model, since he's new to sharing his screen. So you can do it for maybe another hour or so, and then we'll see where we go from there. Of course, there's more theory that we could cover. As I said, the thrusters, we haven't talked about flexible spacecraft at all. We could do that, but I don't want to overload you unless you feel like we haven't done anything particularly new or particularly interesting. So you are more than welcome to send me feedback. And let me know if you want to move on with new theory, or you want to stick to this. Because theory-wise, we pretty much, I've covered what I wanted, more or less. So we can really focus on this, but we can do some more. So I'm asking you guys what you want to do. And you don't have to tell me now. You can think about it this weekend. If you don't feel like using time to do this during class is useful, even though I budgeted quite a bit of hours to do this together, we can move on with other topics or not. But I will need your input on that, okay?
Okay.
And I will definitely try to figure out what's going on with the gravity gradient thing. It's a good exercise for me as well. Any comments, questions? We've gone through a week. So we passed, definitely passed the midpoint. We have 1 hour on Monday, 3 on Tuesday, and another 6. 1, 2, 3, 4, 5, 6. Yeah, 6 on Wednesday, I think. So we still have quite some time together, but no questions, no concerns?
Yes, Professor, just one in the meantime that Marco is doing this.
Yeah.
It's about the BS CMG, if I spelled it good. And it's it concerns the fact concerning the unloading of the wheel, because in this case we could handle this problem, right? In the sense that we are not obliged anymore to rely on thrusters to do this. We can do this by our own. right?
Correct. You can compensate for the undesired torque of desaturating or unloading with the CMG torque effect, yes.
Okay,
So,
and it has never been implemented in space.
Well, because the variable speed quantum moment gyros, as far as I know, they're a little too complicated and risky to be implemented. I'm not aware of anyone who's actually flown them. But you can do it. You could do it. Variable speed. Yeah. You have so many degrees of freedom that you can that you basically can control while desaturating and also do other things such as power accumulation in the wheels. I can send you some papers. Wondering where is this paper from? Journal of Guidance. Yeah. So yeah, just as an example here, this is the professor at Georgia Tech I was talking about, and one of his past PhD students. This is more than, oh my gosh, 15 years ago, and I was working on my thesis and actually was exchanging emails with this gentleman, first author Yoon, and interestingly enough, he's the one who remember when I said that the gamma double dots are never used for control purposes. You can't really control the orientation using the acceleration of the gimbals because the moments of inertia are small. And in addition to that, so now you have that numerical derivative because you're simulating things. But in reality, you don't really take that into account in the control law for the simple reason that your commanded variable is the velocity of the gimbals, the rate of the gimbals. And so if you start taking numerical derivatives of things in real life on signals that may be more or less noisy, it could be a really bad idea. You're just adding, big values that are making things worse. So in other words, in practice, the gamma double dot is not used, that term B gamma double dot. And I was insisting during my thesis time, no, I want to use this term, it's there. And I'm like, well, in reality, yeah, it's there, but it's not very usable. So it was very helpful, I have to say. So let's see. I'm going to save this Journal of Guidance paper, and you can find a lot more probably under today's folder.
Okay, thank you.
Yeah. But this doesn't talk about desaturation though. Let me see. Desaturation. Yeah, things, people have gone are very creative with these things. Let me see what else I can find. This is a very recent paper that I found. For example, control of a thrust vector in CubeSat using a single variable speed control moment gyroscope. That seems interesting. It's from last year, from Milan. And it is something worth reading, so I'm going to save this as well. So yeah, you have a couple of journal guidance papers on variable speed control moment gyroscopes. I'm happy to see that some people are still thinking about them in recent years, because I think there was a huge fuss about them in the early 2000s, and then I'm trying to find there was a paper about power, variable speed control moment gyroscopes, power. Aha, found it. Same research group. Spacecraft adaptive attitude and power tracking with variable speed control moment gyroscopes. Yes, we found it. So this is a very interesting one. They use the fact that you have these additional degrees of freedom to store energy. And so basically the variable speed control moment gyros become a system to control orientation and store and release power at the same time.
But still on CubeSat, sorry.
This was a generic study, not on particularly any Cube spacecraft, and I don't think it was even CubeSats, because this paper is from 2002, so it's a very theoretical paper. You will recognize a lot of the stuff that we have done, such as the control law, that is that WQT, QWQT inverse, etc. But then they add, I guess, other constraints, so that they can play with the transfer of kinetic energy and power, using the wheels as accumulators, basically. Okay. I think it's time to wrap it up for today. So yeah. Monday we'll pick it up from here, if Mr. Grasso is okay with that. I'm sure
sure.
If he has time this weekend to work on it, I mean, I'm sure there will be more to show.
I will try to write the equation.
Yeah, you don't have to, but yeah. Everybody can send me the homework too, please, so that you're done with that one. Any last minute questions, thoughts? So in the folder for today, again, I put 3 journal guidance papers that on variable speed control moment gyros. That could be interesting.
Okay, thank you.
Okay, you all have a good weekend then. It's been a pretty intense week. As I said, feel free to send me comments, feedback. We still have some hours to spend together, and I can adjust as needed. I don't want this class to be boring. I don't want this class to be too fast. I want it to be useful and interesting.
Okay.
Okay. Thank you.